Hello everyone. In this chapter we're going to talk about probability, an idea or a concept that you are already familiar with, I'm sure. You perhaps make probability statements and hear about probability statements almost daily. Where we are in the course is that we have reached, to me, what I exemplify as a bridge that will help us to go to the other side. Now, where's the other side? So where have we been? We have completed at this point the descriptive portion of the course. That is the first few chapters we discussed. The idea of descriptive statistic is to look at procedures that will deal primarily with sample, and that's what we have done. Now, once we cross this bridge, I call probability, then we can go on the other side. The other side is the world of inferential statistics. So probability is what bridges the gap between the two worlds, descriptive and inferential statistics for us. In the world of statistics, the inferential statistics, that is the other side. That's where we would like to make statements about the value or values of the population parameters. We would like to infer to them, and then we'll be able to generalize the concepts, the ideas from the sample statistics to parameters of the population. So before we actually do that, and that's in the forthcoming chapters. So in this chapter, we're going to look at some basics of probability. Now, before we actually define probability, I was going to define some of these terminologies, about 6 of them. First, the idea of what is a data. Well, data is any information that you collect on a particular variable. Okay, so for example, if you take the closing prices of a stock, daily closing prices of a certain stock XYZ, that would be the data that you're collecting. What is an experiment? An experiment is any activity that generates data. So for instance, if you go to conduct a survey, so when you conduct a survey, that survey conduction would be the experiment. And that's pretty much what that is, any activity that generates or produces data. Then we talk about a trial. A trial would be the repetition of an experiment. So for instance, each time that you ask questions on a survey from a different person, you are conducting a replication of that experiment, which we call the trial. So if you, for example, ask 20 people their opinion about something, then that's 20 replications or 20 trials of that experiment. We talk about outcomes of an experiment. An outcome is a particular result. If it's single outcome, then it's singular, and of course you can have many outcomes. That would be the plural form of it. So for example, the reading of cholesterol level for a person, that would be a particular outcome of an experiment. Okay. We talk about the sample space. The sample space is where all possible outcomes are. This would be the universe of outcomes. Anything that could happen in the sample space. So, for example, let's say you play a game of poker, okay, card game. The sample space would be all possible 5-card hands that you could be dealt. That's the sample space, all that could happen. And then we define events. Events are defined in context of the experiments. And usually the experimenter, the person who conducts the experiment, defines these events. It's sort of an after effect. Once you collect your data, you conduct the experiment, and you define these events. And we would like to assess or find the probability of these events eventually. So what is the probability? Once we're done with those terminologies. A probability, and I have it here, is simply the likelihood of something happening or possibly not happening. So for example, I want to know what is the probability that a flight for a particular airline, a flight's going to be on time, or it may be delayed or cancelled. So that would be the simple definition of probability. So it's a likelihood. Now, something about this before I forget. Let's say we determine the probability of showers in the next 2 days in the San Diego area is about 5%. I mean, we're not talking heavy showers, just even a mist. So that probability is about 5%. Now, let's say tomorrow comes, whenever our time frame is for that statement. Let's say tomorrow, probability of showers, 5%. Now, if time comes and that event, whether it happens or not, it does not make a liar out of us. So when we assess probability of something, we're just simply, again, stating the likelihood of it. The idea is that we can make decisions, whether it's personal or managerial or business decisions, under uncertainty. So for example, let's say the probability that the XYZ company is going to beat their earnings next week, quarterly earnings that is, on Wall Street, is 60%. 60%. So I can probably make some bets on the stock moving in some direction that I think is going to move based on that 60% probability. Now, whether that event happens or not, it doesn't mean that we lied or we were correct. It just gives us the expectation of something. If probability of showers are 90%, perhaps based on that probability, I can carry an umbrella with me in case there are showers. Okay, so I just want to point that out. Okay, so let's continue on. Now, how do we actually measure or assess probability? Now here I have these paragraphs. You can read them on your own or print them. But we're going to look at three approaches or ways to establish or assess probability. These are going to be subjective, classical, and of course experimental or empirical probabilities. With subjective is just that. Subjective probabilities are not objective. They are subject to the person that states them. So for example, say, what is probability I get an A in the class? I don't know, 50-50. There you go. What is the probability that I get a raise at my job? Well, you know better how your job situation is. So if I ask that question, what's probability that you get a raise at your job in the next 5 months? You're going to say 80% because I'm up for an evaluation and so on and so forth. Now, in this course, we're not going to deal with subjective probabilities. Sometimes we have no recourse. We have to stay with subjective probabilities because there is no objective means of measuring that probability. The trouble with subjective probability is that each person could have different number. So for example, if I ask, well, what is the probability that the Federal Reserve is going to raise rates in the next 6 months? I could ask 5 economists that question, and I'm probably going to get 5 different answers. So, but that's the nature of subjective probability. The next 2 approaches are more, and they're not more, but they are objective in fact. So first, the classical approach. Now, with classical approach, I have a list of items, 1, 2, 3, 4 things here that are required from a classical approach. First of all, the outcomes must be equally likely. For a classical approach to probability, these outcomes have to be equally likely. That means every outcome has equal chance of being either selected or happening. So there's no bias, there's no favoritism toward a particular outcome. Okay. And the trials, remember, if you conduct the experiment more than once, the trials must be independent. And we're talking about in a statistical means of independence. That means the occurrence or non-occurrence of one outcome has no bearing on occurrence or non-occurrence of another outcome. So pretty much each trial its own outcome, without reliance on the prior information or prior occurrences. These trials must be done identically, so that means you conduct them the same way. And the other thing, this is more of an observation, not a requirement, observation about classical approach. Because classical approach, the probabilities are modeled, mathematically modeled. So if we can model them, these probabilities become exact, in the sense that if I say the probability is 1/3, that is exactly 1/3. It's not going to depend on sample size. For example, with a sample of size 50, I may get different probability than if I had a sample of size 30. It's based on mathematical models, so probabilities are exact if we can model them. So how is the probability found? This is how we do it. If you define any event E, then the probability of that event is going to be, I'm over here, is going to be NE over NS, where N here is a number of, it's a count, number of outcomes favorable to event E over number of outcomes possible in sample space, right? So that's how it's done. And this part of it is where the mathematical modeling comes. These number of favorable over number of possible. These counts could involve complex mathematical counting problems. Now, one thing to note here, that probability of any event has to be between 0 and 1 inclusive. So we cannot get lower than 0%, means impossible to happen. And on the high end, we have 1, which means 100%. At that point, the event becomes a sure event to happen. So here's an example that I have. So the simple kind of in-classroom example, very typical. Let's say we roll a regular die that you're familiar with, the one that you play Yahtzee with, backgammon, and so on, all the dice games. Okay, so let's say we roll a single die. And here, notice I'm defining 3 events. Okay, 3 events. And these are events 1, 2, and 3. You can define as many events as you like. Now, here's how I'm calling these events. Event 1, that I observe a digit less than 5, right? So less than 5, that means I have the sample. Actually, here I have the list of outcomes for that event, each event. Next, to observe a prime number. Well, prime numbers are in this list that I have are 2, 3, 5. Note 1 is not prime. In fact, 1 is neither prime nor composite. They call it a unit. So aside from 1, these are the prime numbers from 1 to 6. Event 3 is to observe an even digit. Well, even numbers in my sample space are only 2, 4, 6. So there you go. So these become favorable outcomes to each event. Okay. Now, probability of this event, number of outcomes, 4. 1, 2, 3, 4. Possible outcomes, I have 6. 2/3. Now, how we report probabilities, by the way, we can report probabilities as fractions, decimals, or percents. Okay. And this would be probability of E2, again, 3 out of 6. Probability of E3, 3 out of 6. So there you go. Each event, I could have 100 events. Each event has its own probability. There's no correlation between these. These are probably, and these are what we call independent events. So each its own. Now, just based on what I said earlier, let's say almost call this 70% chance that this event will happen. So it's kind of a very likely event, isn't it? 70%. Now suppose I actually roll a die and I observed a 6. Well, 6 is not part of the outcomes in event 1. So event 1 has not happened or has not occurred if I observe it or roll a 6. Again, that doesn't mean this number was wrong. It just that gives you the expectation of how likely it was for that event to happen. Whether it does or not, it's not material as far as this number is concerned. Now, by the way, when do we say an event has occurred? Let me mention that. Suppose we roll a die and we observe a number 3. 3. Now, 3 is one of the outcomes for favorable to event 1, right? So we're going to say event 1 has occurred if I roll a 3. Event 2 has also occurred, but event 3 did not occur. That's after effect. After I roll a die and I observe a 3, I'm going to say, event 1 and 2 just occurred. Notice events could have common outcomes as they do these two. 2 and 3 are common outcomes to event 1 and 2. Event 2 and 4 have a common outcome of 2. Event 1 and 3 have common outcomes of 2 and 4. So that's just coincidental. That could be. Now, when do we say an event has occurred, by the way, is when you observe only one of its outcomes. You don't have to observe all of them. So let's say I roll the die and I observe a 5. With a 5, that's event 2, one of the outcomes for event 2. So I'm going to say event 2 just occurred because I observed a 5. Okay. Now let's take a look at the last approach to probability. Now this is the kind of approach that we will be taking going forward. And this is the empirical approach, or empirical probabilities as they call them. Some call these experimental probabilities because they are driven by the experiment. Now anything that's driven by experiment, that means it has a potential to change, right? Because if you take a sample of size 50 of something today, sample size 50 different participants, different subjects, different items, you could possibly get different outcomes, different results with a different sample. So these empirical probabilities are sensitive towards a sample, so they are not definitive and they're not exact, as was the case with classical definition. Remember, with classical definition of probability, probabilities are exact. Once you model them, they're exactly that. So for example, probability of event 1 I have up here. That probability is 2/3. That is exactly what you would expect to happen. It's not going to change if I roll a different kind of die. It's not going to change if I conduct my experiment with different dice. As long as they're all fair and they're all 6-sided, I would expect this number to be what it is. With empirical probabilities, probability that we observe event 1 could change depending on how many times we roll the die actually. Okay, so let's actually see what this empirical approach does. With empirical approach, again, here are the list of things, these 4 items that are particularly relevant to empirical approach to probability. 1, the outcomes again are equally likely. So in this context, that means what do you call it? That means if outcomes are equal likely, it means any particular person is as equally likely to be selected, let's say in your sample, than any other person. So there's no bias toward a particular person or subject being selected. And if we repeat the experiment, remember the trials must be independent. So let's say again you interview 20 people. Each time you interview a person, you're replicating the experiment. So you have 20 trials of that experiment. Because we conduct the experiment, the trials must be done in an identical manner, and the probabilities in this case are not exact but only approximate. And the reason for that is because we have to conduct the trial. So the key difference between empirical and classical approach, right up here, the classical approach here, is that in classical approach you need not conduct the experiment. If I want to know what's probability of a tail, if I flip a coin, I don't have to get out the coin and actually flip the coin. Well, there's a head or tail. There's only one outcome favorable to that event, a tail. So it's 1/2 or 50-50, right? Whereas with empirical approach, I actually have to get out the coin. I have to flip that coin as many times as possible. So let's say on the first toss of a coin, there is no tail. So that probability is 0 out of 1, 0%. Second time, I toss the coin and I do not observe a tail. That's 2 tries now. 0 out of 2, still 0%. You see that probability is kind of a rolling probability. Okay. Now, what actually makes this work, for the empirical approach work, is that it's called the law of large numbers. What the law of large numbers says is that, loosely speaking, if the number of trials increases as you do more and more and more trials, then the experimental probability approaches the classical probability. The approximate probability tends to approach the exact probability of that event happening. So that's what the law of large numbers says. And down here I have how we actually find probabilities. So notice in this expression, I don't have an equal sign. I have this tilde, which means approximately equal to. So the probability is not exact, it's only approximate. It's approximately equal to FE. FE is the frequency of outcomes that actually are favorable to event E when you conduct the experiment. Remember, with the empirical approach, you have to conduct the experiment. And there you have it, divided by n number of trials, and that gives you the probability. Again, the reason it's approximate because the denominator will change each time you repeat the experiment. That denominator is not fixed. It's number of trials. It can be 50, 70, 100, 500, 1,000, million. You see how that changes every time. So this is the kind of probability when you collect a sample and you find probabilities, you're finding experimental probabilities or empirical. The word empirical here means based on data, actual data. Now next we're going to look at a series of properties of probability. We're just going to look at these probability statements or rules based on 2 events, A and B. But they do extend beyond 2. It's just the formulas get more complicated. But this will get the point across. And so here we go. First is the addition probability. How do probabilities add? If you have 2 events, probability of A or B, this is the union symbol here. That means or. So probability of A or B is given by probability of A plus probability of B minus their intersection. The intersection translates into an AND statement, minus probability of A and B happening. This is called the general addition rule. Now, if 2 events are disjoint, that means they share no common outcomes right in here. Means there are no common outcomes between them. Then what happens is this A and B, these are outcomes that are in both A and B. Well, if they share no common outcome, then this is nothing, right? There is no common outcome. So probability of that event would be 0 because there is no common outcome. So this part drops out and the formula actually becomes something simpler for mutually exclusive events. And then we talk about conditional probability. With conditional probability, we're talking about probability of an event occurring or non-occurring given another event has occurred prior to that. So for example, the probability of an accident, a traffic accident, a motor vehicle accident on any given day on a stretch of freeway is, let's say, 20%. That's on any given day, doesn't matter. Now at this point, okay, so let's take a look at actually this conditional probability There is a notation here. I just want to clarify it here in the formula that you see here. And it's this notation A, and then there's a line B, okay, which is precisely right here. Okay, so the line that you see here, this line, stands for a word given. Okay, so the way we read this conditional probability formula is that we're looking at probability of event A given B has occurred. Given B has occurred. So probability of A given B has occurred already is probability of A and B divided by probability of B. And there's also a second formula, probability of B given A has occurred. The difference between these two is the given part. What has occurred? Has B occurred or A occurred? And the difference is in the denominator in both formulas. If you look at the formulas, the denominators are different. Given B, you divide by B. Given A, you divide by probability of A. Now, from this, we get the general multiplication rule actually here. And it's very easy. If you cross multiply in the equation or in the formula for conditional probability right here, if we multiply both sides by, say, probability of A, in this case probability of B, you get these two formulas. Okay, so to find probability of A and B, you multiply probability of A times the conditional probability of B given A has occurred. Again, don't worry about these formulas. We're not going to spend too much time on probability or go too deep into it. Although probability, idea of probability and the topic is very deep itself. However, we just want to know enough to move on to the other side. And this one, I believe, is the last formula here in this chapter we're going to see, and then we're going to look at an example. So what if two events are independent? Well, if they're independent, then the given makes no difference, adds no information to us. Okay, in other words, probability of A given B has occurred will be just probability of A. That given part adds no information, in other words, to the probability of A, whatever it is going to remain. So it's for that reason that this part of it, probability of A given B, is just going to be probability of A. Okay, or in this case, probability of B given A is just going to be probability of B. Given A makes no difference, right? We can just ignore that information. Okay, now that's good enough for our work. And going forward, by the way, like if we ever need to use the idea behind these multiplication rules, we tend to stay with this version of it. Probability of A and B is probability of A times B for independent events. The easier version. Now let's take a look at this idea next. We're going to look at a contingency table. Okay, so what is a contingency table here? A contingency table is it's a cross classification. It's a table, so that means it's got the rows and columns. And usually it shows the distribution of scores for two variables. The variables are usually qualitative variables in the contingency table. So let's take a look at these two variables. So I have a variable gender and variable tattoo. These are qualitative variables. And I have defined here 4 events. H, the student has tattoo. N, student does not have tattoo. M, student is male. And F, student is female. So this is pretty much the summary of this contingency table. This is a 2 by 2 contingency table, meaning it has 2 rows by 2 columns. And in red, what I have here are the totals. So in my sample of size 50, it looks like there are 20 male, 30 females. Okay. Now again, here in part A of this example, I have defined a sequence of events. P means probability, M is for that event, so M means a student is male. So suppose a student is randomly selected, and we want to know the probability of each of these events. So the events in order are male, female, has tattoo, does not have tattoo. That's D. D does not have tattoo. Actually, let me adjust this. M is for male, F female, H has it, and D. Okay, instead of N, let me change that to a D. There you go. Does not. D for does not have tattoo. That makes more sense now. Okay, and then we want to know these other events. M and then the line H means what's probability of selecting a person at random, and that person is male, that student is male, given the person selected has a tattoo. Okay, the one next to it, what is probability that if we select a student and it's going to be a female student, see what's to the right of the line means given that has occurred. So for this event, given we have picked a female student, what's the probability that she has a tattoo? F given H means given the person has a tattoo, what's probability the person is female? M and H means probability that the person is both male and has tattoo. F and D means female and does not have tattoo. And then F union H means female or has a tattoo. Okay, so that's what these are. And then in parts B and C, we want to know if those events, being male and having a tattoo, are those independent events, female having a tattoo, or independents. So if you look at now where these numbers come from, I got all of these directly from the table. So for example, probability of male, for this one, I looked at all the males in the sample. And looks like there are 20 males. So the numerator, favorable outcomes 20, sample space 50. In this case, it's the sample size. So it's 20 out of 50 or 40%. Probability of female, well, there are 30 females, 30 out of 50 total is 60%. Probability of having, selecting a student at random, the student has tattoo. Probability of having a tattoo, well, looks like 20 people, regardless of gender. 20 people have tattoos, so 20 out of 50. Probability the person does not have a tattoo, that would be D, has not. So that would be 30 do not have it. 30 out of 50. Now for the conditional ones, if you look at the denominators up to now, it was all 50, 50, 50, the entire sample size. Oftentimes what the given an event has occurred does is restricts the sample space to only those that have the condition. So in this example, male given the person has a tattoo, well, we only look at the people that have tattoos. It looks like only 20 people have tattoos. We ignore or we discard the other students who do not have tattoo, because we're told the person selected has a tattoo. And within that group, you're going to look at, well, how many are male? It looks like 8 out of 20 in that first row. 8 out of 20 have. That's the probability of the person who has a tattoo is going to be a male. What is probability that given the person is female has a tattoo? Well, given female again. So for this one, we're going to look at the females. In this case, female is going to be 30. Good thing I caught this. Okay, so that's going to be 30. Given female, you only look at females. It's going to be 30 females. And has tattoo, well, let's see, 12 out of 30 have it. So that's what that probability is going to be. Now, 12 out of 30 is not going to be 20%. It's going to be 40%. So again, I'm glad I reviewed this one. So we're going to change that to 40%. Okay. Probability of female given the person has tattoo. Given has tattoo, that's female 12. There are 12 females out of 20 total. That's correct, 12 out of 20. Male and H means choosing a person that's male and a person has tattoo. Now, this one, notice, is not a conditional probability. So the denominator is, again, we're back to 50, 50, and in this case, 50 also. So male and age, M and H, so that's male and has 8. 8 people qualify out of 50 for that event. This other one, female and does not have a tattoo, well, has not, and female, this looks like 18 out of 50. And finally, what is probability of choosing a person who's female or has tattoo? F union H. Well, in this case, let's see. Females, we have 30 females, and we have 20 people that have tattoos, right? In this row. 20 have it, and there are 30 females. Now note, these 12 people are female having tattoo. We're counting these people twice, once in the row total of 20, once in the column total of 30. So we need to remove the duplicate counts, the 12, and the reason for that minus 12. So if I did the arithmetic right in this one, that should be 76%. Okay. And here's I stated the reason for that, to remove the duplicate counts. Now, let's take a look at these for part B. Are the events M and H independent? Well, M and H independent. So if you look at probability of male given H, it's got to be the same as probability of M. Remember, given H doesn't make a difference. So M given H, that was 40%. Probability of male, 40%. So the two events are independent. What about probability of female and H? Are those independent? Well, if you look at F, probability of female, is that equal to female given H? Yes. And another way we can also look at that is we can look at probability of H, if probability of H is the same as H given F. Let me actually write that one for you so you can see what I mean. In here, this is what I mean. So if I go probability of H, is that equal to probability of H given F? Are those the same? And probability of H given F is right in here, that's 40%. Probability of having a tattoo is also 40%, but those are both 0.40. So yes, either way you can test it, and both ways it shows that they are indeed independent. Okay, same conclusion. So that takes care of all of the probability stuff we just learned in this section. Now we're going to end the chapter with our counting techniques. Now we're going to look at the kind of counting techniques that is in the field of mathematics known as combinatorics. So we're going to begin with a simple example. Here, suppose I'm trying to complete a journey from A to C. So here I have, oops, sorry, I didn't mean to do that. So I have A, and I had a line here. There you go. Okay, so I'm trying to complete a journey from A to C, and I have to go through B. Okay, so there are 2 ways to go from A to B and 3 ways to go from B to C. Okay, now the question is, well, how many ways can I complete this journey? Now here I have listed all the possibilities that we can do. Okay, so for example, for instance, I can go this way and this way. That's one route. I can go this route and this route. That's 2 routes. Okay, so you can pretty much see all the possibilities that I have listed down below. Okay, I'm talking about down here. This is how many ways you can do this. So it turns out that there are 6 ways. Now the 6 ways, we actually listed all the possibilities. The fundamental counting principle actually allows us to do this without enumerating or counting all the individual routes. Okay, so here's what this fundamental says. Suppose we have K tasks, these T1, 2, 3, and so on. These are tasks that get performed. Okay, so suppose I have K task. Each task can be done in M1, M2, M3, Mn ways. So in other words, task 1 is done in M1 ways. Task 2, M2 ways. In my journey, the person taking this journey, task 1 is to go from part A to part B, from airport A to airport B. The second task is to go from airport B to airport C. Okay. Now the sequence of tasks, therefore, can be done in M1 times M2, M3, Mn ways. So in this, again, made-up example of mine, corresponding to M, we have here M1 is 2, M2, second task, can be done in 3 ways. So M1 times M2, that would be 6 ways to do this. Okay, and that's and these are the 6 routes, the 6 ways of completing that journey. Now, let's take a look at another example. Let's say in this next example, we want to know how many subsets of size 3 are there from 5 letters A, B, C, D, and E. If part A, repetition is allowed. Now, if repetition is allowed, then if I do this in terms of my tasks, okay, so task 1 is to choose the first letter. There are 5 letters, so I'm going to choose 5. Now, repetition is allowed. So, for example, if I pick B here, I can pick B again and again. So, because repetition is allowed, then therefore, for the second task, 5 ways to do that one, and 5 ways to do that third task. So, the total is going to be done in 5 cubed, or 125 ways we can do this. There are 125 subsets of size 3 without any restriction. Now, in parts B and C, we're imposing restrictions. In part B, the repetition is not allowed, but the order is important. The order is important. So, for example, A, B, C, and B, A, C are 2 different ordering. Okay, and that's what we're saying. So, for part A, of course, there's the answer. In part B, it turns out there are 60 ways of doing this, right? Because our first, second, third task, 5 choice for the first letter. Because we don't allow repetition, once you choose a letter, let's say I pick B, then B is fixed and it's out of the pool. For the next spot, I have only 4 letters to choose from. Let's say I chose A. For the next spot, both B and A are out, so I'm only allowed 3 choices. That would be C, D, or E. So for that reason, if repetition isn't allowed and order is important, therefore there are 60 ways of doing this. Now these 60 subsets, I've actually written them down for you here. Now, notice the one that's in highlight. ABC, ACB, BAC, BC, AC, ABC, BA, or CAB, CBA. These 6 subsets are really the same 3 letters, right? In different ordering. So order is important. That's why we have 60 subsets. And this is again a brute force exhaustive list that you're looking at here. Now, what if order doesn't matter? In other words, all the ones in highlight are really the same. So if I'm thinking about these now being 3 people, I don't care if person A, B, C, A, C, B, B, A, C are in a group, as long as they are in one group. There's no ranking, there's no position, president, vice president, secretary, treasurer, like that. So my selection is not sensitive towards order. Well, in that case, if order is not important, it turns out of those 60, only 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 of those are distinct, meaning different. Okay, so all of these folks are the same folks, right? ABD, ADB, BADB, these are all the same. And all of them are the same. This group selection are the same, and this group of subsets are the same also. So from that, you get the distinct, what we call distinct subsets from a group of size 5. And there's going to be only 10 of them. So this is actually going to help us now move on to the idea of permutations and combinations. Now, before we actually see a formula for what we did in this example, let's talk about factorials. Factorials are very useful in our work, particularly for what we're doing now. So, first, the exclamation symbol, this means factorial. Now, remember, going back to algebra days, you may not, when we talk about factors of a number, we're talking about two or more numbers that multiply. The keyword here is multiply. That multiply to a certain number. Like, for example, factors of 6, 2 times 3. So these are factors. Well, the word factorials, the factor in factorial means we have some kind of a product going on in here. Now, this is a particular kind of a factorization or multiplication, really, in that you look at all the numbers beginning with this whole number. So, for example, when we say 5 factorial, you begin with the number times, because it's a factor. And then you multiply by every whole number down to 1. So that's what 5 factorial is, whatever the product is. When we say 3 factorial, that's going to be 3 to 1. Okay, when we say 7 factorial, well, that's 7, 6, all the way to 3 to 1, always down to 1. Okay, so that's what factorials are. Now, 0 factorial by definition is 1. By definition is 1. And I have not a proof but a justification of why this would be true. So, for example, if you continue this idea, the notion of factorial, 1 factorial would be 1 times 1 less than that would be 0 factorial. And here, this is what we're thinking. If I write 5 factorial as product of 5 times 4 factorial, that would be true, wouldn't it? Because that 4 factorial part is 4, 3, 2, 1. So rather than going all the way to 1, we stop at 4 factorial. So this is what we're doing here. Okay. And if we do that, then you can see that because 1 factorial is 1, and 1 factorial is 1 times 0 factorial, then this suggests that 0 factorial must be 1. Okay. Now let's think about permutations. When we look at subgroups or ordering of items in a group, where order is important, the keyword here is order. If order matters, we can actually think of that as a permutation. Now, in the example above, remember for the letters of the alphabet, where we had these 60, remember these, where order mattered, we had 60 subsets of size 3. Well, these subsets, I can actually work the multiplication rule, and that's what I have done here. If you look at 5, 4, 3, I'm essentially manipulating that because I want to incorporate factorials into this work. So that 5, 4, 3 can be written in this form. Okay, well, in that form, we're going to call that the permutation of n objects selected r at a time, and that's what this formula is. Okay, so in our example that we just did earlier with the subsets, here using the notation, the formula we have here, n is 5, r is the subgroups of size 3, and that's what is used down here. Okay, so this just gives you a formula. So again, you don't have to derive the number of subsets. If we recognize a problem as a permutation, order matters, then we can simply just use this formula rather than do the fundamental counting principle. And what I have done here is I actually have shown it up here. Up here, I showed it with our example. And directly below that, what I have done is I have actually generalized this idea. So this is going to be our permutation formula, and that's what's down here. I'm trying to show you the derivation. If you don't follow the derivation, don't worry. So there you have it. And that's our permutation. Now, Megastat, Minitab, and all calculators just about scientific were capable of doing this. I'll show you in a moment. So here's an example. Let's say we want to do P and R, where N is 10, and in part A, R is 7, and then another separately, R is 3. So in this example, again, I follow the factorial notation right here, 10 factorial, 3 factorial. I use a calculator, but if you want, you can really do it again, brute force, 8, 7, 6, 5, 4, 3, 2, 1, which we really don't want to do this by hand, but I'm just showing you how it can be done. There you go. And if you multiply 10 all the way down to 4, that should equal to 64,800. Okay. Now in part B, the second part of that example, permutation 10 choose 3. Well, 10 3 is going to be 10 factorial over 7 factorial, and that's 720. Okay. Here's another example. In this example, let's say we have 5 students. We want to see them in the front row. Remember 5, so here's my front row. 1, 2, 3, 4, 5. There are 50 students enrolled in the class. How many ways can this be done? And again, if you go by fundamental counting principle, there's 50 ways for the first seat, 49 ways to seat the next 49 students. Once those 2 students are seated, only 48 available for the next seat, and 47, 46. There you go. That's going to be the answer. And the answer to that product is 254 million ways of doing it. Okay, so quite a few ways. And so that's just using fundamental counting principle. Now, we can think of this in light of permutations, because order is important. So I'm just going to use this formula that we have right there. And you can get there again a little faster. So remember, with permutations, order matters. Now, if we remove order from our work, what if order does not matter? If order is not important, then in that case, we can remove those duplicates. Remember the ABC, BAC, all of that stuff. So we can remove those. Oops, sorry. I'm trying to fix this as I go. I just typed these up. That's why there's few typos in there. Okay. Now, if order does not matter, then we can actually reduce the number of duplicates by a factor. Now, for 3 items like the ABCs, if I go back up here, there you go, in highlights. With the 3 letters, there are 6 ways that you can arrange these amongst themselves. That would be 3 factorial. There are 3 factorial arrangement of or subsets of size 3. If your subsets are size 4, there are 4 factorial ways to rearrange those subsets. So, make a long story short, if order doesn't matter, then we can actually, we can actually remove the duplicates, and that's what the denominator of this formula is doing. You see, I have P and R, my permutation, divided by R factorial. That's again the permutation of those objects among themselves. And that gives us a new formula. Okay, and here's the formula. So let's take a look at an example working with these formulas. This formula is formula for combination. Now the way they read it is CNR, combination of n items taken R at a time. So let's say we want to do C10-4, C8-3, C8-5. So just go through these in the detailed computation. That's your 10 factorial. I wrote it out. 4 factorial, wrote it out. 10 minus 4 is 6. 6 factorial, I wrote that out. Now, one thing with factorial, you cannot distribute this exclamation symbol. So it's not 10 factorial minus 4 factorial. That would be incorrect. You just have to do the parentheses inside and then factorial it. And of course, once you do that, then then we are good to go with this. And we can actually cross out the common factors. In the case of 10, 4, notice I have 6 by 4, 3, 2, 1, 6 by 4, 3, 2, 1. Those cross out. The remaining fraction becomes 210. The one below it, here's 5, 4, 3, 2, 1, 5, 4, 3, 2, 1. So, or again, both calculators and the softwares will give you this value. I'll show you how to do this in Megastat and Minitab in a few moments. Okay, now let's look at this next example. In our next example, let me take this actually out of it. There's no number that goes with this example. Okay. So in this example, we're going to look at, it reads, a class has 40 students. 5 students are selected to go on a field trip. How many ways can this be done? Now, when you send a group of people on a field trip, the order in which the group remains or stays together doesn't matter. True? So this would be an example of a combination. So you can do combinations C4, 5, and that ends up being over 658,000 ways of doing this. And that's what this is. So that's how many ways you can choose a group of size 4 from a sample of size 40. Okay. Let's look at the next example. In this next example, let me just hide it a little bit for now. This next example, the question reads, how many ways can you choose 5 mathematics, 2 biology, 3 physics textbooks from 8 mathematics, 4 biology, and 5 physics textbook? Now, if you look at this one, again, we have 3 tasks, right? So this would be like, for example, task 1 is to choose the math book. Task 2 is to choose the biology, and task 3 is to choose the physics book, right? Now, if we multiply those together, we get the combined sequence, the entire task, that is. So the question is, how many ways do I choose? Let's see. I have 5 math, 2, 3. Okay, I want to choose 5 math books from 8. So the question is, how many ways do I choose 5 mathematics textbooks from 8 textbooks? So each of those tasks, once we figure them out, then we're going to multiply them together, and that's going to be the answer. So that's our strategy. So here's how many ways we can do task 1. Choosing 5 textbooks from 8 textbooks. That's alone, that itself is done in 8 factorial over 5 factorial, this right in here. That's how many ways it's done. To choose 2 biology books from 4, that's how many ways you can do that one. And finally, to do the last one, the physics books, there are 5 physics texts. We want to choose 3 of them. That's how many the physics books are selected. How many ways there are. And then the product, of course, is going to be 3,360 ways we can choose these textbooks. So, very interesting. So we're done. This was as far as we want to cover in this chapter. Now, what I want to do next is I'm going to go to Megastat, and I'm going to go to Minitab to do both of these in both of those. And we'll see how the examples work out. So I'm going to pause this for now and bring up Megastat next. Okay, so I'm in Excel now, and I already have Megastat add-in installed. Now this Megastat add-in, I know some of you have emailed me say that Excel does not retain Megastat. You have to kind of add that add-in each time. I'm not sure, why it does that, because again, I'm not in touch with how this add-in, the third-party vendor has worked it, how this works. But on mine, it tends to stay. But then in my other Excel applications, in my other laptops, it doesn't stay either. So sometimes I have to reinstall it. But anyhow, assuming you have Megastat in there, so you go to Excel add-ins and there's Megastat. right? So you click on Megastat. You go to probability. Now in probability here, we go to counting rules. That's what we're doing. And there you go. So if you want a straight factorial, like if I want to know what is 3 factorial, you just click on factorial, and then here just type 3 and OK. And if you do that, there you go. Factorial permutation combination. I'm not sure what this turned out to be. Okay, 3 factorials. Okay, let me actually redo this again. I'm not sure what that is. That's not the right answer. Counting. Okay, so I'm just going to actually click on preview here. Okay, and there you go, 6. Oh, I see. There you go. So in my output, I just typed 3. So the top is n is 3. The bottom is n factorial. That's 3 factorial. So this is the answer. The 6 is the answer here. Okay. And down here, that's the natural log of n factorial. You don't need that. That's just extra information. Okay. So if you want to have the number inside the spreadsheet, so for example, if I want to know what 5 factorial is, if you hit OK, it appears in this output tab. So n was 5, 5 factorial is 120. Again, this is the natural log of it. If you don't want, you can erase it. This is the answer, 120. Okay, now let me change, and let me just, from now on I'm just going to preview that on the screen rather than print it. Okay, counting rules. Now let's say we want to do permutation. Let's do our 8 choose 5 permutation of 8 and 5. There you go, preview. So 6720. Remember my subset of size 3 example. I have 5 letters of the alphabet. I want to choose subsets of size 3 where order matters. There are 60 subsets. Now change that to a combination. Remember when we changed it to combination, the answer was 10. So now make it combination, preview, and there's 10. And let's do 8 combination, choose 5. Okay, backspace. Here is 8 and this is 5. Remember that was our math textbook example. We want to choose 5 math books from 8 textbooks. There are 56 ways to do that. So let's say you have 50 students. You want to choose 5 to send to a field trip. That's over 2 million ways of doing that. So there you go. This is pretty simple. That's how it's done in Megastat. Now I'm going to pause the video and look at it in Minitab. Okay, now I have Minitab up and running. So let's do the same factorial thing with Minitab now. So for this one, I go calculator. And I kind of already have it here because I tried it, but let's say I don't have it. And so this is what you should get, right, when you invoke the calculator command. Now, store results in a variable. You can call it a variable you want. I'm just going to call it, for example, permutations, perm. And then here, expression. If you scroll down the function list, alphabetical listing, P for permutations. You're going to come across and there you go, permutations. Down below here, it shows you the syntax of that function. You can select it or double click. Now, number of items. Let's say we want to do permutation of 8 and number to choose. The number to choose, we're going to go, let's go 4. 8 choose 4, 8 choose 2, 3, whatever. 8 choose 4. And then hit OK. And there you go. Perm 1680. Let's say we want to do a combination. So I'm going to go calculator. This time I'm going to store the result in variable permutation. We're going to go combination. Okay, combination. And we're just going to backspace into that one. Alphabetical listing. This is combinations. Number of items. Let's say I have 50. And I want to choose let's choose what, 50, choose 5. Over 2 million ways of doing that. We did that with Megastat. 50, choose 5. And hit OK. And there you go. So that's how you do these. It's pretty, again, basic, pretty simple in Minitab. So with that, we did it in both Minitab and Megastat. So we're done with this lecture and with this chapter.